Welcome! In this video, we will discuss the diagonalization of the complex Klein-Gordon Hamiltonian. So this is basically the problem 2.2b from Peskin and Schroeder's quantum field theory book. So I'm going to take a bit longer to solve the problem than you may need because I want to make sure that we understand every step. So if you are not interested in the preamble, I will have the timestamps down below, but I do recommend that you watch it because it's going to help you have everything make sense, okay? So the problem is the following. It says, diagonalize the Hamiltonian by introducing creation and annihilation operators, and then we will show that the theory contains two sets of particles M, okay? So the Hamiltonian for the complex Klein-Gordon Hamiltonian we have already found previously, and it is this right there. And as I mentioned, in principle, you could start the problem out by saying, well, I know kind of what the field looks like in terms of the creation and annihilation operators in the just normal Klein-Gordon field, right? When it was the real Klein-Gordon, maybe I shouldn't say normal in this case. And we could say, well, then we could kind of guess our way into the field, which is what some solutions do. But I don't really like it because I feel like when we are at this level of physics, it is good that we take the extra time to derive it. So that's what we're going to do first and foremost. So try to see where this thing comes from. So to begin, let's think about what it is that we are doing, right? We are now in the complex Klein-Gordon field. What that means is that there are now two distinct equations that we need to consider. So now, since phi conjugate is not the same as phi, right? It is not a real field anymore. Now we have two Klein-Gordon equations. So that means, of course, that we now have to be able to write our field. So let's write phi as a real plus an imaginary part, right? So let's say this is going to be phi 1. This is the real part. Phi 1 here would, of course, be Hermitian, plus I phi 2. Phi 2 also Hermitian, of course. And now we can just add a normalization factor in front so that everything works out nicely. And of course, the complex field, so phi star, I guess I should write the x dependence. So maybe let's fix that here. So phi of x, and this is also of x, phi 2 of x. So at least for now, we will keep the dependence. And phi star, well, this is simply going to be 1 over square root of 2. And we take the complex conjugate, so we still have phi 1 of x. But now we have minus I, phi 2 of x. And now what we're going to do is we're going to invert this relation so that we can write phi 1 and phi 2 in terms of phi and phi conjugate. So that's the goal right now. So the way to go about it is, well, just solve this system of equations. I think the easiest possibility is to just add them up. So we add these equations. And by doing that, let's see, we get phi plus phi star. And then we get 2 times the phi 1, right? Phi 2 just cancels out. And now we're going to subtract the equations. And by doing that, we get, so that would be phi x minus phi conjugate. And we get, again, 2 square root of 2. But this time we have I, and we have phi 2 of x. So now from each one of these, we can just quickly isolate the relevant field. So phi 1 of x is going to be, now we can here do a little modification because this is going to be square root of 2 over 2. You can, of course, just multiply and divide by square root of 2 so that we end up with 2 up here. And that cancels out with this 2 downstairs. So we end up with 1 over square root of 2. I mean, you don't really have to do it, but it looks a bit nicer. So I think it's fine. So phi of x plus phi conjugate of x. And down here, we get phi 2 of x. This is going to be, now we get the same thing, but with an I in the denominator here. So 1 over square root of 2i. And then, well, the subtraction. So minus phi conjugate. And finally, we can multiply here and divide by I. so that we end up with an I up here. And this I turns into a -1. So that way we get rid of the I in the denominator, which we never really like to have, right? So with this, we now have written phi1 and phi2 in terms of the fields that we actually want to work with. Now, let's just quickly notice. So notice the following. Both of these fields, so phi1 and phi2, they also satisfy the Klein-Gordon equation. So this is true for phi1 and for phi2 as well. Okay, and the way to see this is simply to plug it in, right? So if you plug phi in or phi2 into any of these, you get some numbers, which don't really matter, phi x, which satisfies this equation, minus phi conjugate, which also satisfies this equation. So in both cases, it's quite direct to see that this does indeed satisfy it. So what is important to note is that when we have the complex Klein-Gordon field, we have a system where we have two spin zero Klein-Gordon fields, right? And they are completely independent. We have these two independent Klein-Gordon zero spin fields. And what that means basically is that we have two particles and they both are going to have a mass of m. And in principle, we could work either with phi1 and phi2 or with phi and phi conjugate, but we are going to prefer to work with phi and phi conjugate. So now what we want to do, just like we did in the case for the real Klein-Gordon field, is that we are going to want to expand our field. So we're going to now go back into the form that we have seen previously. So I'm just going to copy it from what we had before and just add some similar notation. So in the case for phi, I'm going to write I as in 1 or 2, right? So I is going to be 1 or 2 so that we don't have to write this twice. So phi I x. And now the same thing that we did for the real Klein-Gordon field. So we write this as d3k. Now here there are some differences in notation. Maybe we should stick to p. I guess that's fine. You can write this as d3p or d3k. Different books use different notations. Then there's also differences in terms of normalization factors. So you can write this as 2 pi cube, but also another book may write this as 2 pi cube square root of that thing, right? So both things are the same. So don't worry if you have one notation versus the other. It's simply conventions. You may be using a different convention than some sort of book, or maybe even the one that I'm going to be using. So I'm just going to stick for now to this 2 pi cubed. And then we also have this factor of 2, and there's another difference. You may see this as 2 omega p, or you can see this as 2 EP. There's no big difference. It's fine, you can choose whatever. So let's just call this 2 EP, which I think is what Peskin Schroeder tends to use more. And now we're going to want to write this as the sum of plane wave solutions to the Klein-Gordon equation, which we know they are always solutions. And this is the same thing that we did previously. So we're going to have AI, right, just in general for 1 or 2. This is of course going to be dependent on p, e to the minus ipx. Again, you could see this written as ikx. It's just a matter of notation. And then we get plus ai dagger of p e to the ipx. So you can see that each one of these fields, 1 and 2, I'm going to maybe move that a little bit, are going to have their own set of creation and annihilation operators. And of course, notice that the energy here is going to be the positive square root of k squared plus m squared, which is going to be greater than 0. So now what we want to do is that we want to find the canonical commutation relations between these new creation and annihilation operators. So here we are going to base this off of the ones that we already know. So I'm going to just write here, remember. So this is what we used to have. So basing on what we know about these operators already, we can see how they're going to behave. So in our case, we're going to have the following. So in our case, we regard that AI of P and AJ of P prime, this is going to be 0. I just realized there's an equal sign missing there. and that's the same as having a I dagger of P and a J dagger of P prime. So what this basically means is that just like before, whenever we have these things combined, it's just zero. So if you have a creation and creation, annihilation and annihilation, they commute. So yeah, and that is true for both I equal 1, I equal 2. So for both of those cases and for any combination. So that is not really different from what we had before. And honestly, the other case is not going to be too different either. So what we're going to have in the other case is that a I of P and a J dagger of P prime, these are going to commute, they're not going to commute, and the relation is going to be the following. So only if I and J are equal, so if we're talking about the same field here, or the same particle within that field solution, then it's going to be non-zero, right? If they are different ones, so A1 and A2, or rather A1 and A2 dagger, they commute, right? So this commutator would be 0. So we have delta ij, and then we have the familiar del cubed of P minus P prime. So it's basically the same as before, but it is good that we went over it just to make sure. So now that we know what phi I looks like, basically phi 1 and phi 2, let's go ahead and expand these expressions, right? So phi of x and phi conjugate of x, let's expand it in terms of what we know these things look like, and let's use the relations between the creation and destruction operators that we have learned. Okay, so let's begin here with phi of x. So this would be phi of x. So this is 1 over the square root of 2. And then we have phi 1 plus I phi 2. So let's just go step by step. So that would be phi 1. This is integral d3p 2 pi cubed 1 over 2 EP, and then we got a I P e to the minus I P x plus AI dagger P e to the I P x. And then we got the same thing, but with an I, and now everything is not going to be 1, so this was AI. So maybe let's, instead of AI, actually write this, because this is now A1. So A1. And now we have the same thing, but with A2. So I'm just going to copy and paste this. Okay, and now what we can do is we can pull the integral to the outside, right? We can factor it out. So that's going to be integral of d3p, and then we got a bunch of constants, so 2 pi cubed, 2EP square root of 2. And now comes the interesting part. So now we have A1p e to the minus IPX. So let's put everything with e to the minus and e to the plus together. So we have e to the minus IPX. We can move it around freely. It's just a number. We don't really care about that. We don't have to worry about any sort of commutation issues there. So here we will have A1p and A2, so A1 plus A2, or rather plus IA2, right? So there's an I right there, so let's not forget about it. Then we have everything that has e to the plus IPX, and here we would have A1 dagger plus IA2 dagger. So now we can introduce the operators. A of k, this is going to be 1 over the square root of 2. That's going to absorb this part. And this is going to be a factor of the things that we have here. Oh, I didn't close that parentheses. So this is A1 of p plus I A2 of p. And also we have b of p. So this is going to be 1 over square root of 2. And this thing right there. But notice that we want this to be the conjugate version. So we are going to have A1 of p minus I A2 of P. That way, when we actually take the complex conjugate, we're going to get A1 dagger and then minus I A2 dagger, right? So that's why we defined it that way. With that, we get that phi of x, this is going to be, this 1 over square root of 2 is now gone. So now we have integral of d3p 2 pi cubed 2ep, and then we have a p e to the minus I px, and then we have plus e to the, I guess I can do it like this so that it's a bit more orderly. So this would be b p dagger, and then we got e to the I px. So this is basically what we wanted to show. I think I have it written down over there. So we just kind of see the logic of where this comes from. As you can see, the fact that we have A and B as the operators here is simply a consequence of the fact that we now have two particles instead of just one, which was its own antiparticle before, if you might remember. So we have now phi of x, and well, you could also find phi conjugate. Here you can do it in two ways. You can either just plug everything into phi conjugate, in which case you're going to have this little bit of a minus sign there as a difference. Or you can just take the complex conjugate of this, whatever makes you happy, that's fine. So this would be d3p over 2 pi cubed 2ep, and now we got this thing. So now this is going to be a dagger e to the plus ipx. So a dagger e to the ipx, and then we got plus b e to the minus ipx. So that is what that looks like. These are very important results that we're going to be using. And now, just to make sure that this is very, very, very clear, the only non-zero commutator is going to be a of p with a dagger of p prime, and also b of p. So we already saw this before, but I just want to write this explicitly. B dagger of p prime, and these are going to be delta cubed p minus p prime. So these are the only non-zero commutators. Any other combination you see, as we wrote down before, that's basically what we wrote down back here, but I just want to make sure that it's understood because we are going to need this. Every other combination is 0, so keep that in mind. All right, so now let's continue. Okay, so I just noticed that the entire time I was writing 1 over 2ep when it should be the square root of 2ep, so I'm going to make sure that I add a comment to the video, so in case you see that there was a mistake, I do apologize for it. Okay, so what we have to do now is diagonalize this Hamiltonian. So for that, we want to find each one of these quantities. So let's begin with the conjugate momenta. That's simply the time derivative of the respective field. So that's phi dot conjugate. And we can find this, well, simply by taking the time derivative of what we have right here, so of phi conjugate. Now this entire part right there will not be affected since it doesn't have any time dependence, so it will stay exactly the same. And then we go into this. So there's no time dependence in the operators themselves, so we don't have to worry about it, but there is a time dependence in e to the ipx. Why? Because e to the ipx, so rather ipx, that is basically, since we are dealing with these 4 vectors here, this is going to be ip0 x0 minus ipx. And this you can just write as ip0, that's the energy, so that's going to be ep, and x0 is time, so that's this minus ipx. So in the first term right there, we are going to get, so first we still have this a dagger of p, which hasn't changed, and then we have a factor of, if we see the time derivative here, we get iep, and then we have e to the ipx plus b P, and now this time we have a minus sign. So we have a minus in front of everything, so we get a minus IEP, e to the minus IPX. Okay, so with this we can see that we can factor out IEP from this. So let's factor it out quickly. So I'm just going to get rid of it here, here, put a minus sign in between, and now just move things around a little bit. So this we will move to the side. Let's add the prefactor here. So this is IEP, and then we got another parenthesis there, and maybe let's just move this entire thing over to the side. So now let's calculate phi dot, just so that we can get more practice here taking these derivatives, which I guess it could be sometimes tricky because you forget about what's in there. Well, again, we get the same prefactor, so integral d3p 2 pi cubed, or 3 over 2, depending on what notation you are using, 1 over square root of 2ep, or omega p, depending on what notation you're using. And then we got, let's see, a of p, and then we have minus IPX. So that means we get a minus IEP. So we get minus IEP, and then we have plus, this is going to be B conjugate or B dagger of P, and then we get IEP. All right, that should be it. And of course, e to the, oh, I'm missing the exponentials. So this is e to the IPX, and this one is e to the minus IPX. Okay. So again, we can here just factor this out. Okay, and one thing we can do is just to make sure that we get the same sign in here, we can just factor a minus sign. You don't really have to do it, but it is quite normal to do this. So we just factor a minus sign, we put it out there, and that way we have a minus b in both phi and phi conjugate dot. Okay, so now we have this. So maybe let's just quickly put our result in red so that we can find it easily when we need it next. So this is the result here. Okay, so with that, we now need to find the spatial derivatives. So, well, let's go ahead and do that. So that is done, well, in the same manner. We have to take the spatial derivative. Let's begin now with phi rather than phi conjugate. So phi is what we have up there. Maybe it's getting a bit too far away, so I guess I can just make a quick copy and put it somewhere where we can see it a bit more easily. So there, just to the side. So if we want to take now the spatial derivative, again, we get a bunch of prefactors. So integral blah, blah, blah. And now we have, well, same AP. And now when we take the integral, let's take a look at what we have up here. So when there is a negative in the exponent, we get a positive out here. So we're going to get I times P. Keep in mind, that's the vector. All right. And then we get, well, e to the minus IPX. And then we have plus B dagger. And this time, since it's positive, we have a minus sign there. So this is going to be minus IP. Okay. So now we just take, oh, and I can't forget about the exponential. I kind of tend to forget about them, so let's not. E to the IPX. So now let's factor out IP from this. So here goes IP. Okay, so now we want to calculate, well, maybe first let's put this in a red box so that we don't forget about it. And now let's calculate the spatial derivative of the phi conjugate. Now, we could just take this time the conjugate of what we have here. It might be easiest, so let's do that. So that's the same thing, which doesn't change. right? And we could have done this in the previous part as well, but I just like to show you how to do things in every possible way. So that's minus IP, and then we get AP dagger e to the IPX positive minus B, not dagger anymore, just B, and e to the minus IPX. All right, so again, let's just enshrine this in a beautiful red box. There we go. So now we have everything we need. So let's begin inserting it into our Hamiltonian. So in the Hamiltonian, we have phi dot conjugate times phi dot. So let's begin with that. And of course, don't forget about the spatial integral there, right? So the Hamiltonian is integral d3x of, and now just take a deep breath. We're going to do a very long, very nasty computation, but it is not difficult. It is long, it is nasty, it is ugly, but it is not difficult. The only way for you to screw this up is if you are not careful. So just chill, take a nice cup of coffee, cup of tea, know that what comes will be long, and chill. It will be long, but it's not inherently difficult. So just plug in phi dot conjugate times phi dot. So, and a very important thing, since we now have these two quantities, we have phi dot conjugate phi dot x, we have to take into account that there's going to be a momentum P and momentum Q. So be very careful about that. So I'm always going to label the first one. So everything that is conjugate will be P, everything that is not conjugate will be Q. Again, that's arbitrary. You can switch it around if you want. Okay, so having said all that, let's begin. So we have D3P coming from all the conjugates, 2 pi cubed 1 over square root of 2EP, and I'm just going to factor that out immediately. We also have integral of D3Q, and well, 2 pi cubed square root of 2EQ this time, sorry. And now we can actually begin. So those are just the prefactors because every single term has that, right? Since what we are going to be multiplying is this pi cubed, the conjugate momentum here, has that whole factor with P. This one has it with Q. This one has it with P. This one with Q. This one with P. This one with Q. Okay, so that's why we can factor it out. Now, let's now plug it in. So we have this thing. So we have IEP times a dagger P e to the IPX minus, now just to make notation faster, I'm not going to write it in parentheses, I'm going to write it as a subscript. So like that, just to make it a bit faster. So e to the IPX minus BP, and then e to the minus IPX. Okay, and now this is multiplied by the non-conjugate version. So now this is going to be multiplied by this one right there. So now we have minus IEQ, be very careful about that, and then let's see, AQ e to the minus IQX minus B dagger Q EIQX. Okay, so that's the first one. Then we have plus, and now what comes next? Now comes the multiplication of these two, right, of the spatial derivatives. So again, just deep breath. Minus IP, and then this thing, right? The prefactor is already there. That's why we took it out. Otherwise, we have to write it down every single time, and that is very annoying. And then we have A dagger P e to the IPX minus BP e to the minus IPX. I guess I should have used this kind of parentheses just to be consistent, even though it doesn't really matter. And then we multiply by the non-conjugate one. So that would be IQ, not P anymore. So that's now IQ. And the minus sign is already there, okay? And then we have AQ P e to the, sorry, not P, it's Q, AQ e to the minus IQX minus B dagger of Q e to the IQX. Okay, so that's the second one. And finally, we have the third part, which is mass squared times just the fields themselves. Okay, so where is our field conjugate? I believe we left it somewhere. Here it is. So I'm just going to copy it and move it down. Okay, so with that in mind, let's begin. So this would be plus m squared, and now just plug this in. Again, this prefactor we have already considered. So this would be, first with the conjugate, that would be, oops, maybe let's improve that. So that would be AP dagger EIPX plus BP e to the minus IPX. And then we have the other part, which is going to be with Q's now. So that's going to be AQ. I don't like that Q, so let's try again. AQ e to the minus IQX plus B dagger of Q e to the IQX. So as you can see so far, not really difficult at all. All we did was plug it in, but be careful to have one with P and one with Q. All right, and I think I'm missing this parenthesis. There we go. Okay, so now comes step number 2, which is multiply through. So don't panic. Again, breathe in deeply. So first, all these prefactors, I'm just going to write it down and speed this up. Okay, then we have this first part. We have minus I times I. We get minus 1, so we get plus 1, so nothing. Just a plus, it doesn't matter. Then we have EP times EQ. And then we have the product of these two parentheses. So this parenthesis with this one. And here, be very careful that you don't mess up the order, because there might be commutatory issues, so be very careful. So we got AP dagger e to the IPX AQ e to the minus IQX. So that's the first one. Let's now, so that's that times this. Now that times that. So then we have minus AP dagger e to the IPX BQ dagger e to the IQX. Now we have those two ready. Let's move on to the next one and be very, very careful here, right? Step by step. Now we have minus BP e to the minus IPX and AQ e to the minus IQX. And we have one more, which is this one. So this time we have a positive, so plus BP e to the minus IPX BQ dagger e to the IQX. Okay, so that's that first line. Let's move on to the second line. So that would be plus. Here we have again minus I times I. That's going to be plus 1, so we can ignore it. And then P times Q. So that is P times Q. No, they are both vectors. I guess I should add that line there. And now let's begin. So we have AP dagger and then e to the IPX, e to the IPX, and then we have AQ e to the minus IQX, and then we have minus AP dagger e to the IPX, BQ dagger e to the IQX. In the next one, now we have minus the following, so minus BP e to the minus IPX, and breathe in AQ e to the minus IQX. We have 1, 2, 3, so we need the fourth term now, so that's plus BP e to the minus IPX, bq dagger e to the I qx. Okay, and now we have just one more term. That would be the mass term here. So that would be plus m squared, and now we multiply through. That would be ap dagger e to the I px aq e to the minus I qx, and then we have plus ap dagger e to the I px and bq dagger e to the I qx. Now we multiply this with this, so we get bp e to the minus I px aq e to the minus I qx, and finally bp e to the minus I px and bq dagger e to the plus, so I qx. There we go. Okay, so it may look absolutely atrocious, but let's take a quick look at it, because we have ap dagger, ap dagger, ap dagger, IPX, 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 AQ, 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 e to the minus IQX, minus IQX, minus IQX. So these three are all the same. Okay, interesting. Then we have BP, e to the minus IPX, BQ dagger, e to the IQX. The same thing, the same thing. So that is quite interesting. What else do we have? Then we have this, which is the same as this, and it is the same as this up to a minus sign. And then we have this, which is the same as this, which is the same as this up to a minus sign. So there are a few things that we could factor out. So let me just quickly rewrite the constants here. So here, let me just do this as intuitively as possible. So we know that this term, so, well, this here is just going to be a number, so we could move it around, but we're going to respect it. So we know that EP, EQ, and P dot Q and M squared, all of those terms are multiplying this plus this, right? All of those are multiplying those two quantities. So all of them multiply AP dagger e to the I px, AQ e to the minus I qx, plus BP e to the minus I px, BQ dagger e to the I qx. All right, and then we have these intermediary terms. So then we have plus, and this time these are multiplied by EPEQ and P dot Q. That's true. So EPEQ plus P dot Q. But now there is a difference, because now there is a minus sign in the M squared. So we have to write minus M squared. Okay, so let's now work on this. So we have to copy these terms. So we get minus AP dagger e to the IPX, BQ dagger e to the IQX, and then we have minus BP e to the minus IPX, AQ e to the minus IQX. Okay. So another thing we can do is pull out this minus sign right here. So let's write this as a sum, and we put the minus sign in front, right there. Okay, so we are making a lot of progress, but there's still more we can do. So we could combine the exponentials, right? So we can write this as e. So this is e to the I p minus, so this is e to the I p minus qx. And now let's just move it to the side. This part right here is e to the minus IPX IQX. So we can write this as minus IP minus Q. So we can write this as e to the minus I p minus q x. Okay, and again, move this to the side. Now down here, we can do the exact same thing, except that here we have e to the I plus. So this is e to the I p plus qx. And down here we have minus. So this would be e to the minus I p plus qx. Okay. And the reason why I wrote it with a minus outside, which may have seen a bit unnatural here, for example, I guess I could fix the way my q is written here so that it's easier to read. So qx parentheses. The reason why I did that is because we have a little thing, and this is a massively important thing for you to remember and to know. We have out here integral d3x over 2 pi cubed of e to the I, and well, we have two different things, but let me just use this as an example, p minus qx. What is this thing, my dear viewer, dear learner, dear member of the Nick Heumann University? What is this? This is simply the Dirac delta cubed of p minus q. You must know this definition, okay? It's very important, and it will come up literally all day long. It has already come up many times. I think I've stressed this out already, but in case you didn't watch those videos or forgot, I tell you once again, learn this if you don't know it already. So that is important to know. And another very important thing is that this is the same as having d3x 2 pi cubed e to the minus I p minus qx, right? Since the Dirac delta really only cares about the point where they are equal, the minus sign doesn't really matter. And you can also see this as you are integrating over all of space, so you can just change x to minus x. There's several ways to go about it, so that's one point. And just to make this very clear, we also have d3x 2 pi cubed. This is e to the ip plus q, right? This is another thing we have in the second line. This is simply Dirac delta of p plus q. And this is, of course, the same in the case where we have a minus sign in front. Minus I p plus qx. So what I'm saying here is that we are going to take this part, well, only with one of these 2 pi cubes. So we are going to have a 2 pi cube remaining. And we are going to use these things. So this will go away, this will go away, this will go away, and this will go away. And they will be replaced by something else. So let me copy paste because I don't feel like writing all of this again. So instead of all of this, what we now have, well, let me rewrite this line and this and 2 pi cube. So what we now have is up here, we have del cube p minus q, and down here we have del cubed p plus q. Now, what does that mean? That means that we now rewrite this entire thing, but changing p to q in the upper line and p to, or, well, you can change p to q or q to p, doesn't matter. But changing one for the other, basically. So in this part, p and q have to be equal. In this part, p has to be equal to minus q. That is what's going on. So let's rewrite this. So we have the Hamiltonian is now going to be, well, p and q have to be equal. So now we only integrate over one single value of q, which is when it is equal to p. So that means we are only left with d3p. Then we have, well, 2 pi cubed, that hasn't changed. And now we have the same thing. So the square root goes away, 2ep. I'm going to stick to p for now. You could choose q if you want. Then we have ep squared plus p dot p, so that's simply p squared, plus m squared. And here we have ap dagger, ap plus bp, bp dagger. And then we have this other term. So then we have minus, and here be very careful because now we have to put p to minus q. So then we have e, or I'm going to do it the other way around. So q to minus p. So EP, well, EP, e minus p is the same thing. So it doesn't really affect in this part. Then we have p dot minus p. So that would be minus p squared. And then we have minus m squared. And let's see, then we have a p dagger, b here minus p dagger plus b p a p or minus p, and there we go. However, notice something very important. EP squared is exactly p squared plus m squared. So this entire thing here is 0. So notice how we have been simplifying this expression. So now what we are left with is only this part. So now we have Hamiltonian is, well, d3p 2 pi cubed. And here also let's use that same thing. So since EP squared is p squared plus m squared, this thing is simply 2 times EP squared. So we have 2EP squared over 2EP, and then we get AP dagger, AP plus BP, BP dagger. Here we get a nice little cancellation here, right? This and that simplifies. So we end up, well, just with EP times that. And in principle, this is already our diagonalized Hamiltonian, which is very, very nice. You can see this nice little form is kind of similar to what you saw in the quantum harmonic oscillator. It's very similar to what we saw in the previous case for Klein-Gordon in the real Klein-Gordon field. But there is another issue here, right? So what we can interpret is A dagger A or B dagger B. Interpreting B dagger is not really something we can do. So while this is not incorrect, that is not the form that we want to have. We want to have this as B dagger B. So we are going to use the commutator here of B and B dagger. So we know that B P and B P dagger, this is simply B P B P dagger, which is what we have right there, minus BP dagger BP. So we can flip this. We can write what we had right there, which is this part. So we can write BP BP dagger. This is equal to the commutator itself, BP BP dagger plus BP dagger BP. So let's plug that in. So with this, we get that the Hamiltonian is going to be integral of d3p 2 pi cubed, and then we have EP, AP dagger AP, and then finally BP dagger BP. And here we have the commutator. Now this is a very similar thing than what we saw before in the case for the real Klein-Gordon field. And this is a bit problematic in principle because we have now an infinite term, right? We have this infinite term right there. So what this is just going to be, that is what we're going to understand as the energy of the vacuum, right? And this is an infinite amount, but it is an infinite amount that we cannot measure. We can measure differences in energies, so it's not really going to affect us, and we are ultimately going to drop it. And this will disappear once we begin actually using time ordering. That's kind of the whole point of time ordering. It gets rid of that. But yeah, this is going to be our final expression. It has this additional infinite term that we have to take into account. But other than that, we get this nice finite Hamiltonian, which we can actually work with. And we can see that we have two sets of particles, right? We used to have simply something like this. Now we have one for each particle, and they both have mass m. So there we go. I hope that this video was useful to you. As I mentioned, all we did was plug things in and use their properties. And it's a very, very good exercise so that you can get acquainted with some of the basic mathematical frameworks of quantum field theory. So yeah, if you enjoyed this video, please make sure to leave a like on the video, comment and subscribe. And maybe even consider checking out my Patreon or my Twitch stream. All the links are appearing here, rotating. And also, they're going to be in the description down below. So thank you very much for watching, and I'll see you in another video.